Okay, so caught me in the middle of trying to put down my glass. I'm going to do, it is so hard to squeeze a talk into 30 minutes, but I'm going to do what I can for this. How am I doing for audio? This might sound a little bit awesome. I'm going to do my best to yell. If I lose my voice mid,
squeeze the mic, please.
Squeeze the mic? Okay. I thought we thought the mic was a little bit distorted. Damn. Alrighty, we'll do that anyway. So hey, look, I'm Casey, and I'm going to move around a lot. Forgive me for the video purposes. All right, so I'm Casey. I joined Joyent just relatively recently, so I figured I might as well introduce myself. I do product management, but at Joyent you have to be an engineer to do product management, pretty much. Before this, I was an engineer, so that's how I passed muster there. I was a customer of Joyent, and that's the important thing. I got really excited about what Joyent was doing, bringing together a couple of things that I am going to talk about, but I promise you it's not going to be a sales pitch. Got excited about it and wanted to be part of it. So moving on, how many people know what Joyent is? Okay, there's some plants over there in the audience over there.
Totally independent.
Okay, totally independent. I saw some hands over there. All y'all deserve t-shirts if I had them, but I don't. And the rest of you would deserve them too, but I don't. Everybody gets a cookie, but no. All right, so Joyent, we build software to manage infrastructure. Right? We provide some infrastructure, but we build software to manage infrastructure so you can run your code on the best infrastructure around. Right? We want really high-speed infrastructure, and so the lies I'm going to talk about today are going to be biased by some of the decisions we've made about how to build this infrastructure. But let me just share with you that you can run this in your data center or ours, right? So you can host it in our cloud, run it in your data center, and by the way, hey, it's totally open source. Well, mostly open source. So go to GitHub, download it, install it, put it on your laptop, put it on some spare hardware. There's somebody in the room who's done that. I don't see them. Anyway, I'll let them self-identify, especially if you're out for drinks later. And so there we are. You may be familiar with Joyent because of our involvement with Node.js. We love Node. Just about everything that we write that isn't written in C is written in Node. We've been involved with it for a long time, and we offer support for some major enterprises for Node. And recently, if you've heard about us, you've heard about how much we love Docker. And that's one of the reasons I joined the company, because I love Docker too. And so some of the biases that I'm going to talk about are from the perspective of containerization is awesome. Containerization makes scale superiorly possible. And so what we've done is we've taken our container native, our infrastructure, and added Docker support. We call that Triton, and that is the end of the sales pitch. The rest of what follows is about the decisions we've made and the lies we've told about this. But just to level set and understand this, how many in this room, I just want to get we're not here at a Docker meetup, but I want to know how many folks have deployed Docker in production? Hands? People who know what? People who know Joyent have deployed Docker. That's amazing. How many people have played with Docker? They got boot to Docker on your laptop. Okay. So there's some people who are going to understand what we're talking about in terms of containers, and as I reference Docker. So what about microservices? Sometimes a scary word for architecture, but are you building apps and let's
real microservices or bullshit microservices?
I'm going to take a really flexible definition to it. Really flexible definition of microservices. Do you think that that's a thing for you, right? Any hands? Anybody yes, I'm all micro. Yeah, okay, a few people. Man, it's a wide room. I got to make sure I'm looking both ways before I cross the street. Alrighty, did I lose? Oh no. I'm on a black screen at the moment. This is also a company town, so I got to ask, anybody here from Azure or AWS? Woot. Thank you for self-identifying. All right, so make sure you come out for drinks later because, I don't let you drink. And not just because I want to avoid any rotten tomatoes thrown my way, but also because, hey, if there's anybody here deeply involved with the internals of Hyper-V or Zen, you might have nits to pick. So I just want to invite you to do that. But anyway, so there we are with the introductions there. The thing I'm getting at, and the title of this is The Lies We Tell to Our Code, and the thing that I want us to understand is that lying to our code is practical. Everything that we do in the computer is really fictional, so lying to it about what we're doing, making some leaps across the previous logic that we held, that's essential. It's incredibly practical. And the thing is, we can do that, right? We can do that without worrying about the morals of lying about it, right? But it's not like there are no consequences whatsoever, right? So what we have to remember is that we really go wrong when we lie to ourselves, right? So lie to your code, but never ever lie to yourself. All right? And so to get us warmed up on some of this, some of the earliest common lies, not by any means the earliest lie, but some of the earliest ones are about virtual memory, right? So we pretend that there's some extra memory there mapped out to disk. I use this, again, to level set because there's a lot of, the notion of how we're lying about this has changed. If you've followed some things, especially Paul Honeycutt, you know how opinionated people can be about virtual memory, right? Especially, whether the application should use it or not use it. And this is a great read, but I've only got 30 minutes, so let's move on. And the reality is, for most of us, I don't know anybody who doesn't just do this for many of their apps when they're trying to optimize, especially in the cloud. And the reality is, we want better quality of service than you can get by ever having anything other than that. So skipping past that lie, and this is going to be a long catalog of lies, some of them we're going to get into a lot more detail than others, but skipping past that lie, here's one that is almost entirely harmless, right? This notion that, this one core is in fact two cores, right? And so that works. Of course, it depends on the operating system being complicit in the lie, even though it looks, and you might forget that when you look at things that it's actually got two cores. The reality, however, of course, is that having two pretend cores for each core does not actually get you double the performance, in part because you're not doubling the I/O, right? And also because of the nature of how it works. So the best, if you believe this lie, the best thing that you can do is compress all of your I/O and use those extra virtual cores to decompress it in the CPU. So you can optimize your I/O chain and get back to better utilization of the CPU. So again, remember what lies you're telling and how to best take advantage of them, and also remember when you're lying to yourself, right? And so now you can understand why I'm asking about those people who understand Zen and Hyper-V deeply inside. One of these things, the reality about lies, of course, the reality is many of us are deploying in the cloud. And a lot of people in this room, just another show of hands, how many of you have code running on virtual machines out there in the cloud? Okay, it would be easier, of course, to ask how many don't, but I'm not going to bother. The reality is all of us do, right? And so how do we optimize our code to run in virtual machines? Virtual machines are one of the biggest lies ever, but it's the lie on which we built most of the cloud, most of the past 10 years of infrastructure, right? So one of the frustrating things is how we lie about the virtual machine. So we all know and we think about some of how this works, but when you're virtualizing the hardware, there are instructions that the operating system would otherwise execute on the CPU that you can't let it execute on the CPU. So you've got to intercept those instructions, right? And there's somebody who's going to argue with me about it, especially if there is anybody who understands the internals of Zen, that's going to say, no, we'll get to that. But you can't let the operating system just run willy-nilly across the CPU because it's got multiple operating systems running on it. So you've got a lot of work going on in the hypervisor to prevent it from doing those things, right? Which is where we get to this other lie, this notion that there's something about the difference between a type 1 and a type 2 hypervisor, right? Who can tell me the difference? I don't want to ask. And so the point that I'm getting at is there is no difference because no matter what you're doing, your hypervisor is actually a kernel, which is basically what the operating system is. That's mediating all of the interactions between all of those things. So whether you got a type 1 or type 2, you've actually got an operating system in there. And you've got a lot of resources in that operating system to manage that interaction. All your I/O is going through it. You've got a lot of things that are going on, especially as we talk about para-virtualization. By the way, which is faster, hardware virtualization or para-virtualization? Okay, hardware? Okay, another point in the room. Consistently every time? Yeah, alrighty. And so here's the funny thing, right? It started out that we were like, hey, let's virtualize the whole hardware. And it was like, oh, but it's so hard because we have to trap those we have to trap those calls to the CPU and remap those, rewrite those. And it would be a whole lot easier if the operating system would just not make those calls in the first place, right? And that's where we got to paravirtualization. And then they're like, oh gosh, but actually, that's not as fast as if instead we modify the hardware. So the underlying CPU, if it could be aware of the virtualization and remove it, so lie upon lie upon lie, right? And so we get to the point where we started with hardware, moved to paravirtualization, moved back to hardware because it's way faster, all right? Sometimes we're in one of those transitional states where it depends on your workload. Of course, the other thing is, well, we'll get to the other thing. So I'm going to, throughout this conversation, when I talk about hardware virtualization, I'm not making any distinction between hardware and paravirtualization. Hardware virtualization, as far as I'm concerned, is the same thing. The awesome thing about hardware virtualization is it's ideal for tinkerers, right? And so you can mess with everything. You can spend a lot of time trying to optimize every darn thing. Now, why does playing with the clock source improve performance on hardware virtualized machines? Or actually, well, again, hardware virtualized, paravirtualized. Answers? Clock source? Silence. Silence. So many people here, and myself included, are deploying into hardware virtualized clouds at times, and we don't even know about this one. Now, so a Joyent alum, Brendan Gregg, he says by playing with the clock source, he can get up to a 30% reduced CPU utilization, right, and 40% reduced latency, right? That's huge. And that's playing with the clock source. So what is going on with the clock source to change I/O latency and reduce CPU utilization? Well, the other thing that we have to look at is this particular conversation here is about skew in the real-time clock. So if we talk about clock source, we talk about skew in the real-time clock, and we talk about how you change that clock source, perhaps going from one source that is ticking faster than another source. All of them are still real-time. It's just the number of interrupts that you get per second that changes. You start to think about what's going on with the underlying hardware virtual machine and whether it's getting all the CPU it thinks it's getting, right? And so when you're in an environment in the cloud, you can almost guarantee that they have oversubscribed the CPU. And so that's the other lie that we're telling to ourselves. Well, that we're telling to our code. We're buying a machine with so many virtual cores, and we think we're going to get those cores. As it turns out, part of the issue with clock source and part of the issue with skew is that we don't get those things, right? So how does this work out? So one of the things is actually skewed real-time clock is one of the easiest pathologies to deal with, right? So we can correct that periodically. But sometimes not getting the interrupts you expect and not getting the response within the time that you expect, because an operating system is a hard real-time app that absolutely has to get its responses within a certain time or else it crashes. And so oversubscribing CPU when you are hardware virtualized and have a guest OS is a very, very, very delicate balance of keeping that guest OS thinking that it will continue to work. Right? And so the issue with keeping the guest kernel working effectively is a huge job of the underlying hypervisor kernel. A lot of competing kernels here. It's like I'm trying to see. Anyway, forget. All right, so let's go back to this about I/O latency, right? And so think about what happens if your OS, your host OS, is not getting the interrupts. Well, sorry, not getting the CPU cycles as it needs. Those interrupts are incredibly costly, right? And so some of the advice, and again, this is why I want to invite AWS people to drink with me tonight. But some of the advice here is, what do you do? Well, first thing you do is you actually maximize your buffers, right? And so you let the network right into the buffer, right, which is DMA access. You let the network right into the buffer before, and maximize the size of that buffer before that CPU, before that OS has to get a response. Right? And so in doing that, what you can do is reduce the number of timeouts that you get and the number of transmission failures and receive failures. Right? And so you do this because you can no longer expect the OS to get the cycles that it expects to get, to behave the way it was originally tuned for the I/O and the drivers that it's got. And so another thing you can fiddle with, including clock source, is the size of your network buffers. All right, so we're not going to talk about this, especially in 30 minutes, but don't ever oversubscribe memory. It inevitably means you're going to swap out to disk. And then your OS doesn't even know, your guest OS doesn't even know that it's swapped out to disk. So if you are aware that you're in a memory oversubscribed environment, run elsewhere, whether it's Joyent or wherever, run elsewhere. You will be so much happier for it. So overall, and I love that there's some Basho in the room. I love reading this support document about, look, we know you guys are going to deploy on a hardware virtualized cloud somewhere. We just wish you wouldn't. If you must, however, keep in mind that you'll need a whole lot more instances than you would real hardware. And they just shrug their shoulders. It's a document that goes on point after point about how it almost doesn't work. And yet, maybe you could do it if you double your resource consumption everywhere else. So the conclusion here, and remember my biases, the conclusion here is that hardware virtualization is really bad for performance, right? All sorts of reasons. You get bad network performance, you get bad, everything. So let's move on. So there's an alternative here, because I don't come here just to complain. There is an alternative, a different kind of lying that we can do, right? And so we talked earlier, I happen to love Docker, right? And so what does Docker do in the context of virtualization, right? I see some nodding here. I know you got it. Docker eliminates that guest OS, right? And so by having multiple independent instances all sharing the same kernel, you get some magic. And the picture behind me, by the way, I just did a Google image search and stole a whole bunch of images for this presentation. So it's all going to be up online later, and hopefully we can avoid lawsuit because I credited people. But the point is, in this case, we're talking about the I/O chain. Right? And so much shorter I/O chain just to get to disk or network, but that's not the whole point. So the simple idea here, right, is that we've got an operating system, and operating systems, I don't know, since the 60s, in the earliest days of Unix, and even before that in other timeshare systems, have really proven themselves at being really good at separating processes and users and protecting them from each other, right? And so let's build on that. Instead of reinventing the hardware and emulating the hardware, let's build on what the operating system can already do, right? And the things that it does that we don't really accept as lies, build on that to go further and pretend like there are whole, not hardware machines, but whole machines that have the appearance of having isolated users and software running processes. So you add namespaces, a lot of namespaces in some cases, and it works pretty well, right? And so out of this deal, right, you get a lot more workload density, right? So you can significantly improve the performance of your workload, of your software, reduce latency, all of that on the same hardware. Or you could significantly reduce the amount of hardware required to serve the same performance. This is totally awesome, right? Well, and you got to wonder, why are we not all doing it? It is Earth Day, thank you. Why are we not all doing this? Why are we not going container native for Earth Day? And sadly, it's because, I'll wait for the picture, it's because we're still doing our containers inside VMs almost everywhere, right? So of the people who are deploying containers, except for some of the plants, how many of them are running on bare metal? Okay, another plant.
Black Tower, Big Life, within half a go.
And so this is a challenge, right? You can't enjoy the benefits of container virtualization if you're running them inside a virtual machine. This is so sad. And why are we doing that? Well, the reality is when we take a look at how these things are, some of the namespacing and some of the security requirements that make OS-based virtualization work are really new in the Linux kernel. And this particular statement that in some of the release notes is perhaps prescient. And that turned into a surprise last week, that turned into a surprise last week where some people were like, hey, wait a minute, actually user namespaces are not implemented? And this is last week? And we've been using Docker. Some people have been using Docker in production for a long time now, 2013 in some cases. Wow, mind blown, boom. And so, yeah, it's crazy. This is why multi-tenant bare metal hardware exists almost nowhere. Because if you were depending on the services of the Linux kernel to secure your bare metal, it's more of a hope and pray than a actually being able to sleep at night situation. So there is an alternative. For just about every problem, I'm going to offer you an alternative. And so how is it that I can stand here and tell you that containerization can work? Well, the issue is, in the earlier one, those kernel namespaces and those security facilities that entered Linux kernel in 2013 entered the Solaris kernel sometime 15 years ago. And they've been in use since then. In fact, they've been in use at Joyent for almost a decade, right? So Joyent launched on Open Solaris using Solaris zones almost a decade ago. Well, launched a while ago before that, but anyway. So take all that. We've had these containers in production for a long, long time. Now the difference is, I'm not going to tell you we had Docker, right? We haven't had Docker. What we have had is the containerization serving infrastructure containers that looked, acted, and behaved in a lot of ways like a virtual machine on the inside with all the performance of an OS-based container on the outside, inside as well. So this works by having all of these security features baked into the kernel. Remember what Sun Microsystems was in the height of the first .com boom? And all of the big-headed investments that they may have decided to make at that time that finally came out and were released sometime after. And you can think about how big a problem it is to rewrite the kernel, pretty much, from scratch to support OS virtualization. And they invented a lot of things along the way to help this. So dtrace is one of the things that came out at the same time. An important facility for, thumbs up on dtrace, you get a t-shirt, if I had some. And so dtrace, which gives you visibility into every system call being made, right? When you do a set of work, you can see every system call being made. And so you get that ability to actually audit what you're doing. Hugely important to being successful at this. And perhaps one of the reasons why it's hard on other operating systems to get there as well. I hope everybody gets there. That's not my worry though. So all of these things add up to bringing secure, multi-tenant, bare metal, OS-based virtualization to Joyent's offerings. But for the folks who do know what Joyent is, you may be like, oh, wait a minute, didn't you just tell me that you're not running the Linux kernel? So how am I going to run my Linux-based containers? Especially, how am I going to run Docker? Well, that's a really good question. But we can tell more lies about it, right? Because we're here to talk about the lies that we can tell. And so, what is a kernel except for an API definition, right? And a set of services and things that you expect out of that API. So if you could make one API pretend to be another API, awesome town, right? And so, you're looking very serious. You're like, I don't believe him. And you shouldn't, because I'm telling lies, right? How can you believe anything that I would say? But no, seriously, we can tell lies about what system calls are out there, right? And so this is called branded zones in our world. And so it started years ago with the need to be able to present. So actually consider what was 10 years ago a long-running container might have been running for decades 10 years ago, right? Because they're banks using this software and they don't ever want to change anything. So if you have a long-running container, you don't want to have to upgrade the operating system underneath it because people didn't do that back then. And so what was required was they had to have a way to upgrade the underlying host, OS, without having to upgrade the applications running in a container on that. Right? And so what they invented was this mechanism called branded zones. So initially it was a way to run, I don't know, SunOS, back when there was the transition from SunOS to Solaris, and different versions of Solaris, run those in zones on top of modern versions of Solaris. So the system call translation, somebody said, hey, wait a minute, we can do that for other kernels too, not just our own. So, genius idea. And they said, you know what? RHEL 3, let's do that. Remember, this was almost a decade ago. So this system call translation is ancient in internet terms. It existed, and then didn't really, you know, kind of went underground for a while and has been resurrected. And oh my God, it's awesome. We got modern Linux kernels just all emulated up out everywhere. And so this is the thing that you want to press me for a demo on because it's not something that we can only talk about so much. You want to see it. If we have time in the questions, ask for it. We will do that. But moving on, past lying about our system calls, I want to move on to another thing that affects performance in the cloud, right? And so block storage, right? Just level setting here, keep in mind what block storage is. And so you take this environment where you have multiple hard drives and you want to make them and present them to the host as a single hard drive. Yeah, simple block storage faking. You can take that idea and be like, well, why do the hard drives have to be in the box, right? And so, yeah, that's genius, right? We'll take everything that depends on the data and we'll move the CPU over here and the data over there, and somehow that's going to make everything better, right? And I don't know whatever came of that except for slower performance and a whole mess of pain. Have drinks with this guy. He's in the room later. Just pointing him out. I wouldn't know that. Anyway, yeah, so all sorts of pain comes from moving the data away from the CPU. So again, know when you're lying, know when you're shooting yourself in the foot, don't do it. But the cool thing here is that it's not so much virtualizing the block store that matters as virtualizing the file system. A virtualized file system is absolutely required for any kind of scale in the cloud. Virtualizing the block store, that's nothing, right? But the thing is, we actually made the mistake of thinking that we have to use these storage appliances, which had different file systems, and you could export it as block stores that could then be recognized as native file systems on our VMware hosts or wherever. And so don't do that. We've actually been virtualizing stuff on the file system for a long time. Hard links, soft links, what is that but lying about where our data is? All right, so not that that's software-defined storage, but just keep in mind, we lie to ourselves, we lie to our computers. What really matters here and why this matters for scale, right, when we talk about Docker, right? And so every Docker image has multiple layers. It starts with the base image and then you do something to it and that creates another image and you continue and it stacks all up so you get multi-layered images. And the fact that this one's only four layers deep on top of the base file system, that's nothing. I mean, a lot of them have a lot more layers than that, which is cool, right? This is awesome. And what happens is those layers are actually shared among different running containers and then shared so that you don't have to download duplicates of another container. So all of us who are like Ubuntu 14.4 base image, which is a pretty fat base image, but that's okay. I use it all the time myself. What it means is you only have to download that Ubuntu 14.4 base image. You only have to do that once for, you know, for everything that demands it at a time, which is cool, right? So what we got to do, though, is you can only write to this new virtual layer that's on top of all those layers. So when you make a write, it's copying the data, the underlying data, and you're modifying not in the underlying layers, but on the top layer, right? And so Docker's first version of this was based on AUFS, or was AUFS, which is pretty cool in that it just kind of worked. Actually, it's represented by different folders on the host file system, which is cool, you know. Unfortunately, it also means that there's a really lousy performance because, hey, it's file-based copy on write. Your performance fails as you add multiple layers, and as the size of the file that you're modifying changes, because it has to dig through all of those layers, find that file, make a copy of it on the new layer. It gets kind of messy performance-wise. And one of the things that .cloud, now Docker, figured out was, in order to get reasonable performance out of this, just don't write your data to that, right? And so before they ever had this notion of data containers, they were like, hey, for performance, just put your data over there on a separate container. And so if you go and look at many of the database, official database containers from Docker, what you'll see is in the Docker file a definition for a volume, all right, that's aside, separate from all of this layering. So you can get reasonable read-write performance with those database stores. It's not like these are the only two choices, but in the interest of time, keep in mind, I want to tell you about ZFS, which takes all of the lies that we tell about file systems, wraps them up, says, you know what, some of these lies are no longer relevant, right? And actually a wonderful conversation I was having just earlier tonight about you come into every new thing thinking, inheriting the lies you told yourself about the last thing. You try to, I don't know, you try to make cars work like horses at first. feed them water. But no, the point is that that it takes a while to figure out the environment that you're in, and use that and maximize the opportunities in that environment for your advantage, right? And so ZFS was one of those attempts, one of those big-headed attempts to try and remake everything. And the awesome thing is, it works, in fact, right? Well, I wouldn't be here talking about it if it didn't. But it does a lot of great things. Even better, to the extent of the lies that you can tell, you can take a set of disks, which are called a pool, right? And then you can add additional disks, especially SSDs, so you can add a write-optimized pool. And it's like, yeah, it's all just disks, all my writes will go. And then it'll write through from the SSD and serialize those random writes to the spinning spindle storage and get much higher performance. So really great high performance opportunities there because it knows how to tell all sorts of lies. That's the point there. We could spend hours talking about ZFS. It's pretty sexy stuff. But the point here is that it does block level, a native copy and write at the block level. So you're taking a large file and you're modifying a small portion of it. You don't have to copy the whole file. You only copy, the one block that changed. Right? And so it does this. It supports thin provisioning. You're working with a huge pool of disks, but actually you're provisioning a file system. And so a file system right now, you think you're actually working with a slice of the disk when you make a file system, when you provision that file system. Of course, that's a lie. That's proven to us when we symlink something, and we're like, hey, yeah, inode or hardlink something, and you're mapping those inodes. There is no physical mapping of the disk. It's all entirely logical. So why should the volume be so hard to change, resize, up and down, and most importantly for the use of being able to very elastically, quickly spin up containers and kill them? Why should the file system, being able to have a unique file system, independent file system with independent user namespace for each file system, why should that be hard, right? And reality is, it's just, oh yeah, okay, new file system there, easy, on top of that pool of disks, cool, right? And so we do this, and well, I just made a really important point there. So let's go back to Stephen Wardley discovering that, hey, wait a minute, there are no user namespaces on RHEL, recent RHEL, as of now, last week. And Solomon chimes in and says, well, let's zoom in on Solomon here. And it's like, oh yeah, look, actually shared file systems, as happens in containers, actually are really problematic with the underlying file system structure, file system that we have. All of these things don't work. You can't do what Docker does, actually, if you do have namespaces. And so there's this underlying security problem in the way Docker works. Now, I'm not against Docker. I'm just saying there are implications to how the file system works in your ability to quickly and thinly provision unique file systems for each container. If you can't do that, you're in trouble. So what I'm saying here is that with ZFS and the ability to quickly, thinly provision these things, we are in a golden spot for containers and doing it securely. But we're not done, right? So we've got containerized virtualization, right? We've got file systems that are virtualized to securely support that. What still happens, especially in the Docker world, and even in some cases in VMs, we don't have NICs for these things. And so how frustrating is it, right, that you spin up a container and you look at that, you do a Docker inspect on the container from in the host, and it's like, oh yeah, that's its IP address. And then you try to go to that IP address, and then you realize, no, actually, with Docker on Linux, you have to go to the host's IP address with the port mapping. So there's this parallax problem with the networking inside a container. Real problem. If only we could virtualize the network in some way, right? And so one of these solutions, it's kind of awesome. There's Weave, which does some great things. On the other hand, it's also like a dog barking opera, because what it's doing is it puts the interface into promiscuous mode. It's capturing everything that's going on that interface, bringing it in, bringing it out of kernel space into user space, inspecting it, perhaps encapsulating it, and then sending it on back out. So I'm not going to ask. If you are using Weave, I would say it turns out that you're consuming one full core of the hardware machine that you're on, and you're probably getting perhaps 10% of your wire speed in doing so, right? And so you want to have, if you have networking, slow networking is not effective, especially in the data center. It wasn't effective when we were trying to do wide area networking on a modem. Slow networking in the data center is going to kill your plans. Microservices will not work. They don't work with high latency, they don't work with slow network. So building something around virtualized network that doesn't perform, well, that's like shooting yourself in the foot. And that's one of the rules about lying. And so what can you do here? Turns out some of these very old technologies that we've been talking about is this network virtualization. It's part of what we're doing. So Crossbow actually uses hardware acceleration in the NIC, which means that not all the NICs are supported, but it uses hardware acceleration in the NIC to present virtual NICs to every container. This means every container can have its own NICs, one or more, and IP addresses on those NICs. And you never have to worry about port conflicts. You never have to worry about the parallax problem. Sorry, I'm totally standing in front of you, so you can't read this. And you don't have to worry about the parallax problem of when you look at the host, you look at the container on one host, it looks like, oh yeah, there's the IP, but no, actually you got to use the... Anyway, so you lose the parallax problem, you get what you're expecting. And then what we've added on top of that is software-defined networking. So, so Crossbow, what it did was virtualize the NIC, which was great, but it meant somebody, basically what you're doing is you're using predefined VLANs. When you virtualize the network, software-defined network, what you're actually doing is giving every user their own layer 2 network, and for every container you get a private IP address on that, a unique private IP address on that layer 2 network. If you ask for it, you also get a public interface. So, all right, we are almost done. Hold your breath. Whirlwind to almost wrap up. So the next thing is, well, we're actually lying about Docker, right? And so you can't just run Docker, because Docker inevitably you're running just, in a lot of cases you're running just on one machine, and no real application runs on a single host, right? And so how do you do that? One of these choices, and I love it by the way, I love all these things, don't mistake that. Docker Swarm, which does an awesome thing. What it does is it takes a number of remote Docker API endpoints and virtualizes them, lies to us to pretend that they're actually just one. So you can do a Docker run and push and schedule across all of those different remote Docker API endpoints, which is kind of awesome, right? And so the same thing that we're doing on our laptops, perhaps with Docker Compose, you can then point to your Docker Swarm virtualized API endpoint and deploy those, preserving what we love about Docker, which is that we can build and test on our laptops whole composed applications preferably, and then do that out there. Think about some of the alternatives that actually don't use the Docker native API, actually do out-of-band communication and don't assume that. Now we're no longer virtualizing Docker, we're actually creating a whole new API. And it turns out implementing those and running those on your laptop can be really difficult. Now, moving on from that though, what we've done at Joyent with Triton, the logo we had on screen earlier, is actually really similar to Swarm. We actually did it first, but so what we're doing is we're taking all of the compute nodes in the data center, or if you're running on, so public data center, all of the compute nodes in our public data centers, or if you're running on a private data center, your own hardware, all of the compute nodes on those data centers, and we're virtualizing those as a single Docker host. Right? Without needing to set up and use Swarm, it just presents itself, right? Because the Docker API is not an infrastructure management API. It's an API to launch applications, right? And so infrastructure needs to be below the applications, and the applications run on the infrastructure. If we rearrange those things, those layers, and put the application API underneath the infrastructure API, it can be really frustrating. So we've elevated it to the data center level, and you can just run and launch applications on the whole data center as easily as you can do that and run them on your laptop. So again, like with Docker Swarm, you preserve this laptop to cloud ability, which I think is pretty exciting. Whew. Okay, so this is my rest slide, and I finally get a chance to drink this. So the thing that I want to make clear, yes. So we all tell lies, right? We're telling a whole bunch of lies. I'm here to talk about the lies that will optimize our ability to scale in the cloud, right? And that means running in containers, not virtual machines, right? And so look for container native options there. Right now, I'm honestly only aware of Joyent as the only one, but again, you can build your own cloud on bare metal. You can do that because if you're not running container native, if you're running in VMs, you're losing a lot of that value. You're contributing to global warming. Don't do that, right? You know, watch out for security issues. They are solvable. I think we have some pretty simple and easy solutions for that. You know, and really, when it comes to how we lie, the great philosopher Missy Elliott had some really good notions about evaluating the value, right? And doing the various gymnastics necessary. Who's going to sing this with me? Evaluating the work and the gymnastics necessary to do this, right? Understand that there's no shame in this. You're accomplishing some sort of thing. Just make sure you're ahead of the game, right? And so, again, just that's my rules for lying. Thank you, and remember Joyent for all these great things, and ask me questions. I think we have time. How are we doing on time?
Yeah.
Question? Yes.
So, if I understand correctly, Docker is a fancy way of bootstrapping a Docker infrastructure in VirtualBox so that you can run a VM that is your host for your Docker containers.
Mm-hmm.
It'd be really sexy if there was a boot to Joyent that did the same thing with OpenSolaris.
It's called Cole.
Excellent.
If you go to github.com/joyent/SDC, it'll give you instructions on how to install Cole. You lose, of course, the advantages. I mean, keep in mind that you're running something that expects to run on a whole data center on your laptop. If you don't have 16 gigabytes of RAM, you will cry. Sad, sad. So the question was, can you boot to Triton? I think is the wrap up, and the answer is yes. I would not recommend it as a way to do Docker development, application development in Docker. It's not very lightweight, as I was describing. And so boot to Docker, I think, may be a good solution in that you can do everything except for the network simplicity. You don't worry so much about the security implications of the code that you're running when you're doing that development. And you can use tools that should hopefully deploy pretty cleanly from there. But you can also run your own private data center, old hardware. I have some Triton running on some NUCs, Intel NUCs, you know, these little 4-inch computers, and so that's pretty convenient. They give me a lot of fun and performance in that way. Yeah.
The primary concern was that because you are simulating the Linux kernel and not actually running it, it's going to have different characteristics, and debugging problems will be challenging if you don't have an option.
Absolutely. Okay, so the question is, it's based on the likely inevitable differences between a simulated Linux kernel and an actual Linux kernel. Not going to argue. Not going to lie about that one. I think they're minimal, but how do you debug those? And so, yeah, exactly. You can, in fact, do just as you asked. It's also worth noting, Joyent we bill our containers by the minute. And so spinning up really small containers, 128 megabyte containers that are ideal for microservices, is pretty easy. And so spinning up and testing a container, you know, for any amount of time can be pretty quick and easy, and low cost is the important thing. And you can also test, you know, how is this going to work on a, I don't know, 3264 process vCPU machine? And you can try that out without having to buy the whole hour on it, right? Anyway, so there are some choices there, but most importantly, the ability to run this, it is open source. You can run this on your own hardware. You can see it, take it apart, test it on your own. Absolutely true. Cool. I see another point. Where am I? Ah, there you are.
So I'm just curious, how to fight with noisy neighbors from the DSKY perspective? Because if you're running containers on bare metal, there is no way for you to isolate DSKY at all.
So I love that you asked that question. I have, Mr. Bisson, my Twitter handle / Simple Container Benchmarks is one of my containers, and I cannot get it to complete on hardware virtualized environment, well, basically any Linux environment that doesn't have way more CPU assigned to it than it should. When I try to run 3 of them in parallel, even 2 of them in parallel doesn't work, right? And so that very same container, I can run it on a single compute node, more than 100 of them in parallel. And the reason for this is exactly what you're getting to. C groups do not effectively, and I don't want to bag on Linux because there's some great stuff going on, but C groups do not effectively manage resource utilization, especially I/O performance. And so the assertion, I think, is correct for Linux. One of the things, so Joyent started with Open Solaris a long time ago. One of the things, and there are a lot of them I think that we've built, but one of the critical ones here is we've built I/O quotas to manage that, to make sure that everybody gets fair I/O in the same or similar ways to how we manage CPU utilization. And so that did not exist before we added it, and it does solve that. Excuse me, it does solve that problem, I believe, and I believe it does so very effectively. So I don't challenge your assertion entirely, just that it's limited to certain kernel implementations. But thank you for asking. I like it. We should let's do a demo at the bar of that one. All right. What else? Other questions? Oh yeah. Oh hey, and we're cutting. There's like anyway. So thank you for coming. Awesome, and good night. Thank you very much.